Okay, in this video, we're going to talk about second order linear differential equations with constant coefficients. So that's going to be a differential equation of the form a times the second derivative of y of t. Usually the second derivative, the marks are after y, plus b times y prime plus c times y is 0. This is a homogeneous, I should say that we're going to talk about how to solve the homogeneous differential equation. Right. So this is where a, b, and c are real numbers. So an example would be something like 2 times y double prime minus 7y prime plus 6y equals 0. So we're looking for a function y of t that satisfies this equation. And the theorem is that once you know two linearly independent functions that satisfies this equation, then you can get all of the solutions. So the theorem is if y1 of t and y2 of t are two linearly independent solutions to this equation, which I'll just call star. Okay, this is the homogeneous second order linear differential equation with constant coefficients. Okay, then you actually know all the solutions. The general solution to the differential equation is y is equal to c1 y1 plus c2 y2, where c1 and c2 are real numbers. And we're looking for real valued functions. Okay, so we just need to find y1 and y2, and then once you find y1 and y2, then you know the general solution. So now how do you find just two linearly independent solutions to the differential equation? Well, the idea is to that you can try, so how do you find y1 and y2? So the idea is to try y, so this could be y1 or y2, equals e to some constant t. So e to the rt. Say. So r is some real number. And it turns out that you will, in many cases, be able to find y1 and y2 as e raised to some constant times t. So what happens if you try that? Well, what happens if you plug... So you're trying to figure out what r will make y of t. So find r that will make y of t a solution to the differential equation. Well, we need to find y prime and y double prime and then plug them in. So the first derivative is what? It's r times e to the rt, right? Because of the chain rule, you have to multiply by r. And then the second derivative is going to be what? Well, it's going to be r squared e to the rt, because you have a constant r which you pull out, and then you have an e to the rt, and then when you take the derivative of that, you get the other r comes down, and then you get r squared. So r squared e to the rt. And so therefore, when you plug it in, you're going to get a times y double prime, that's a times r squared e to the rt, plus b times y prime, so that's b times r e to the rt, plus c times y, which is c times e to the rt, is 0. And now you see what's nice about this is you can factor out the e to the rt, and then get, when you factor, you get ar squared plus br plus c is 0. So what we've shown is if r satisfies ar squared plus br plus c equals 0, right? If that's true, then y of t equals e to the rt is a solution to the differential equation. Let's put a box around that to indicate that's important. Okay? So let's do an example. Let's say you wanted to solve y double prime minus 5 times y prime plus 6y is equal to 0. Well, so here our a is 1, our b is -5, and our c is 6. Right? We're trying to match it with this format. When you match it with that format, you get a is 1, b is -5, c is 6. And so therefore the quadratic is going to be r squared minus 5r plus 6. You want to find r that satisfies this equation, equals 0. So we can factor this. R minus 2 times r minus 3 is 0. So r is 2 and 3. So therefore, y equals e to the 2t and y equals e to the 3t are solutions to the equation, to the differential equation that we're trying to solve. And so now we have two linearly independent solutions. And so therefore, by the theorem, the general solution is y of t is c1 e to the 2t plus c2 e to the 3t. And this will always happen when you have two distinct real roots. So if you have two distinct real roots, right, this is what we have, two distinct real roots. R1 and R2, so your R1 is going to be 2, your R2 is going to be 3, or, it doesn't matter. Your R2 could be 3 and your R1 could be 2, right? Just whatever. You take one root, you take another root, you call one of them R1, the other one's R2, and then you get the solution out of it. Okay? So when you have two distinct roots to the quadratic equation, it's really easy. More complicated is when you have, so remember, when you have a quadratic equation, okay, if you have ax squared plus bx plus c is 0, you have three possibilities. One of them is that you have two distinct real roots, R1 and R2. That's one possibility. Another possibility is that you have one repeated root, R. So a good example would be if you had, x squared minus 6x plus 9 equals 0, then you're going to get x minus 3 squared is 0. and you get x3, x equals 3 is a repeated root. It's when you separate it into linear factors, right? When you factor the quadratic, the same linear term appears twice, because this is x minus 3 in parentheses squared, right? It's x minus 3 times x minus 3. So that's a repeated root. The 3 is a repeated root. And then the other possibility is you have two distinct roots, but they're non-real. They're two distinct non-real. So these are complex roots that are not real. So a good example would be if you had x squared plus 1 is 0. Well, then the roots are going to be I and negative I, right? And we need to talk a bit more. So we know how to solve this one when you have two distinct roots. But what happens when you have one repeated root and when you have two distinct non-real roots? We'll talk about those in a future video. Okay, thanks for watching.